Okay, can start. Hello, everyone, and thank you for joining us today for our Quantum Speaker webinar series hosted by ATARC's Global Quantum Working Group. I'm Lily Chen. I'm one of the group's government co-chairs. We are very excited to welcome Christine Wiedbrook to speak with us today. Christine is the CEO and the founder of Xanadu Quantum Technologies, a Canadian quantum technology company. In this talk, he will talk about Xanadu's roadmap to 1 million qubits using light. If you have questions, please use the Q&A feature. We will save Q&A for the end. So please, Christine, you can start now.
Thank you, Lily, and thank you for inviting me and looking forward to telling you more about what we do here at Xanadu. We'll begin by talking a bit about the industry overall and why quantum computing, and then talk about our hardware, our roadmap from a high level, and also our software stack, which is called Penny Lane. So thank you again for joining me. The idea with quantum computing, we kind of like this analogy in terms of looking back at past technological revolutions. With the PC revolution, the mid 70s, and also the internet, early 90s, we at Xanadu, and also a lot of people in the industry, believe that quantum computing has a potential to be just as transformational as these industries. What's interesting is some parallels there where, with PCs in terms of applications, it was really hobbyists in the early 70s that really took to it. And applications didn't really start to the very late 70s with spreadsheets and documents. And that obviously took off beyond that, and games and so forth as well. And the internet is something that's so transformational that, hopefully quantum computing will also be very similar. The other idea of quantum computing in terms of the motivation is the world will always want more computing power. It seems very unlikely that someone or a group of people say, look, let's stop there at trying to boost the computational power of a device. It's grown dramatically over the last few decades now. But there is an issue with wanting more computing power, is that we've essentially reached the end of the road for Moore's law. So the Moore's law was prophesized, I guess, in 1965 by Gordon Moore. And essentially, it's had some variants over particularly the first decade or so when it was developed, as every 18 months, the power of a computer will double. And so this actually goes back, it's kind of cool seeing it go back over not just the digital era, but over 120 years of computing power. It's kind of held from the mechanical systems, computer systems, all the way up to integrated circuit. So it's effectively ended in its purest form, perhaps. But computing systems do get more and more powerful, and there's ways around Moore's law, at least in the traditional sense, through using core computing, cloud computing, and so forth. But the idea here is that it's going to fully slow down, and we need some form of replacement. And obviously, as you can guess, we believe that replacement is quantum computing. And when I say replacement for the speed of computing in terms of its evolution, classical compute will still be around. Quantum computing will go hand in hand with classical compute. But in order for its most advanced achievements in terms of the field of computing, quantum computing really is needed to continue human progress over the next 10 years and also this century. Really imagine if we didn't have computers today and all the progress that we wouldn't have had. And so we see hopefully quantum computing is having that sort of hindsight as well. So what are some of the things? Well, really the field is still working on what some of the biggest breakthroughs and early cases will be for quantum computing, but you can see some of them listed here. Overall, though, you can think of the fields of logistics, pharmaceuticals, so new drugs being developed, quantum chemistry and material design. So for us, that's what we're working on, and more specifically, next generation battery development. That's a big one, and also financial applications as well. All of those four fields are very big, and understanding exactly where quantum computing will sort of develop within those is still ongoing research. For us, we've decided to focus just on batteries because we believe if you take into all the sort of knowledge we have at the moment, probably the first use cases will be in quantum chemistry, the lowest hanging fruit. What you can do is say 100 logical qubits or 100 to 1,000 logical qubits, so about 1 million physical qubits. Other ones are still possible, but most likely beyond this decade. At Xanadu, we always come back to our mission. It's kind of our North Star. It helps us make decisions, and often it's easy to get caught up in the details. So this allows us to come back to the big picture. And it's to build quantum computers that are useful and available to people everywhere. So it shows you what we do. We actually build these quantum computers. We actually use light or photons to build our quantum computer. One of the more unique approaches, although it's gaining in popularity the last few years by other companies as well. We make them useful by having teams work on our software, and our software stack is called Penny Lane. And also we have a dedicated algorithms team, as I mentioned before, working on quantum chemistry applications. And available to people everywhere indicates the idea that, how do we get into many users possible? Initially, that will be over our photonic quantum cloud platform. We were founded just over 8 years ago, headquartered in downtown Toronto. Most people are based here in Toronto, although we do have people working throughout the world, including in the US. And currently we have 212 people, I guess, as the current count. And so far we've raised over $275 million. 250 of that has come from venture capital. So it all comes back to success, obviously, and success we define as success in the hardware. The kind of easy intuition behind that is, you can work on algorithms, you can work on software, which we're doing both of those, and they're very important. But if you can't build, us or anyone else can't get to 1 million physical qubits and essentially show quantum commercial advantage, then what's the point? At the abstract level, you just got to provide a solution that's faster than the status quo. And so it all comes back to the hardware. At the core, we're a photonic quantum hardware company. And so we believe these three things, given that. One is the fastest path to 1 million qubits will ultimately win a massive market. Now, we don't believe that there's only going to be one winner. We hopefully believe we're going to be one of the winners, but there's many great approaches out there. But like with anything, you'll see a lot of consolidation, mergers and acquisition, a lot failing, like any sort of new industry. And there'll be a few winners to 1 million qubits. We do think, though, that in terms of scaling, our photonic hardware and photonics in general really offers the best path to scaling. And as mentioned, there's a few winners, with others being too late, meaning they can potentially get to 1 million qubits. But if you don't get there in the first kind of clump of winners, then perhaps it'll be too late. And obviously, a lot of approaches, like any industry, will fail as well. So these other approaches, we've kind of identified 5 of them. We've obviously put ours first and in a bigger circle than the rest. And that's photonics. It's not just us. PsiQuantum is another well-known one doing photonics as well. Other approaches can be broken up into superconducting qubits and circuits, ion traps, neutral atoms, and spin qubits. And you can see some of the great companies there listed under the very different approaches. But, roughly speaking, you can think of either building a quantum computer out of photons or electrons. And as I said, both are very well worth approaches to be pursuing, and all of them have their pros and cons. At Xanadu, we're full stack, as mentioned. So we do everything from the hardware all the way up to the algorithms. And in between, we have the rack scale integration, so systems integration, and also the software and the cloud platform that I mentioned before. We're a fabless company. So what that means is we do all the chip designs in-house in Toronto here, and then send them off to different foundries that we work with around the world. Everyone talks about the great things about their approach, and we have some too. The biggest challenge is loss. So if we fail, it's because we haven't been able to overcome loss in the system. So loss can be thought of as really sending light through a medium, whether it's a waveguide, fiber optics, free space. not all the information that's encoded on the light makes it, say, from A to B. And you've got to deal with that. That's the loss aspect. And so error correction and fault tolerance, that's a big part of it. Working with foundries based on our chip designs, that's another big part of it. And all the stuff in between, including the optimization of the type of architectures that we use to build our hardware. So that's really the biggest side of things. Once we get the chips back, though, a lot of it is on us with packaging and systems integration, as mentioned before. So I mentioned the biggest challenge for photonics, not just us, but anyone using light. And that also applies to people outside of quantum computing. So those building networks, those building sensors and so forth. What are some of the benefits? Well, there's quite a few. No cooling is required for the computational stage. In fact, we believe it's a race to 1,000,000 qubits, which will be a quantum data center. That's really the size that you can contain 1,000,000 qubits. And it'll be made up of a traditional like data center. So it'll have like thousands of server racks that are all networked together. But inside these server racks, we'll have quantum computers. And we anticipate about 10% of this data center needs cooling, but 90% doesn't. Definitely, the computational side doesn't need any cooling. For us, it's the state preparation side. So that's a big benefit. I mean, a lot of investors like to hear that, but really when it comes down to it, it's a benefit of iteration. You can move much faster because you don't have to wait for these cryostats or cooling systems to heat up, to cool down and then heat back up again. And then also the ability to miniaturize things is really key as well. The less cooling you need is key. And also the fact that, there's a lot of classical compute here as well. And so other companies will have to figure out how to put things that weren't normally meant for cryostats or cooling systems like FPGAs, GPUs. And a lot of that control electronics also needs to be in the cryostat. And so cryostats or the cooling systems in general need to get bigger. Another great benefit of photonics is we can actually go to large foundries like TSMC and Global Foundries, who in fact we work with Global Foundries and others, and they already have the tools and have spent hundreds of millions of dollars on these tools to actually take our chip designs. Huge benefit because, when you do want to come to the mass production phase, which is if we're successful, assuming we will get to that phase, then you don't want to build your own foundry. You want to work very fast, save a lot of time and money. Photonics also offers error correction flexibility, so you don't have to be locked into your decision of error correction codes at the beginning stages. The networkability is very big, and modularity, because, as I mentioned, this data center will have a lot of server racks that need to be networked. And this is networked between independent quantum systems. And so that comes for free, kind of more naturally is probably a better way of saying it, because you don't have to go from one server rack to another. It could be two electronic systems via fiber optics, because going from one medium, electronics, converting to photonics and back to electronics, that's been done in traditional data centers. But quantum mechanically, it's a whole different story. It's very, very hard to do. It's probabilistic. It's noisy, lossy, all these things. So that's going to be a challenge for non-photonic based approaches. Still a challenge for us in terms of loss, but it's just more natural to go from photonics to photonics to photonics again. We've saved a lot of time and money too with being compatible with telecom. We didn't have to invent the laser or fiber optics. This interesting slide really shows you some of the use cases. And to be fair, this is kind of an indication of the industry overall. We spend a lot of our time working with car companies and battery companies working on next generation batteries. The good thing about that is we don't have to convince them to do that. A lot of them have small to medium-sized quantum computing teams already. And the idea there is, once you have this quantum data center, how do you use it to give them better ideas for candidates for new materials that can be used in batteries that create things, 10 or 100 times faster in terms of the range, charging capacity, speed with which it charges, while still maintaining stability and the safety properties that you would want as well. We also have a team dedicated to quantum machine learning, and we work with people on that. And that could be for a range of applications, not necessarily batteries as well. And that's actually how our software stack started, PennyLane, a quantum machine learning package. Continue with the use cases too. Maybe some of the ones I haven't mentioned. AWS has Penny Lane pre-installed on its great bracket quantum offering. We also work with NVIDIA. NVIDIA is interesting. They're basically looking to essentially how do you get more and more people using their GPUs, which they don't have a problem with at the moment, but thinking about where quantum computing and GPUs overlap. And they overlap in two places. Kind of interesting. One is the actual building of the quantum computer. You're going to need GPUs for the error detection correction side of things, the classical compute that based on that compute result gets fed back into the quantum computing for error correction. And then also how do you simulate quantum systems? So if you want to come up with a new quantum code or algorithm, you actually have to simulate this whole system. And obviously, well, you better hope that you can't simulate it efficiently on a traditional classical system, because you wouldn't need a quantum computer then. So you use that for a lot of testing of ideas and simulating how they come out as well. So in terms of the US presence, which is applicable for our call today, a couple of things you can see on the left. We have a US subsidiary now, Xanadu USA, and we also have an office now at AIM Photonics, a small office, but we're building out a team in the US there. Foundry work is obviously very key for us. We're working with AIM and a few others in the US and throughout the world, as mentioned before. NIST, we've had a creator with them. Actually, the creator that says 2020, I believe that was our second or third creator. We've renewed it over many years. And we started working with NIST, I believe, in 2017. They've been fantastic for us. We've loved working with them. That's on our detector systems, our photon number resolving detectors. We've also had an investment in one of our past rounds. I believe it was our last round with Incutel. They've been great support, and also been awarded a couple of DARPA awards. The first one in 2021 was for software in our Penny Lane, and then recently awarded as one of the collaborators on the Inspired program in 2024. So it's great to see our expansion through all these different means, and also being partners. You can see some of the ones there, Chicago Quantum Exchange and others. We've also, Oak Ridge has bought time on our quantum cloud platform as well. So, and also working towards hopefully getting another AFRL, but this time another creator, but this time with AFRL as well, and also part of QEDC. One of the big things that's really put Xanadu on the map in the last 2 years and really helped us raise our last round of funding, Xanadu demonstrated quantum supremacy, or quantum computational advantage, as it's also called. And it was also it was only the third time it was demonstrated. First time famously by Google, who did a tremendous job there, and then also by China. And third time ever was by Xanadu. Made it into Nature, and it was the first time demonstrated by a startup, first time in Canada, which we're proud of. And also it was the first time anywhere in the world that it was put on the cloud for commercial use. We had that available through Xanadu and also on AWS cloud through their bracket system. And that was available for 1 year there. So the team was really proud of it. And it's kind of it's been, when it first came out, it would have taken, at the time, the world's fastest supercomputer, which was in Japan. It would have taken, for this problem that we went head to head with between quantum and classical computers, it would have taken the world's fastest supercomputer 7 million years to solve this problem. And our Xanadu quantum computer, which we call Borealis, solved it in 2 minutes. And obviously, you can think of all the energy savings, if you'd ran this, for 7 million years. We used 216 photonic squeeze qubits or modes of light for this. And at the time, it was the largest demonstration of quantum supremacy. And this 7 million years have been brought down also by classical compute, which we thought would happen, and a lot of great job by doing supercompute improvements and optimizations. But it really showed you what's capable of quantum computing, joining those other two great experiments. But also it helped us put us on the map as well. Lily mentioned our roadmap. So our roadmap for fault tolerance is more at a high level, but each of these can be brought sort of decomposed into more specific tasks, which we've done. But at a high level, the first stage is really improving the components, the performance of the optical core components. So beam splitters, phase shifters, squeezers, and so forth, detectors. These are things that we'll continue to work on going, over the years. Loss, as mentioned, needs to be improved on all of these components. We're on track, though. Our goal is to build this quantum data center, or you can think of FTQC, fault-tolerant quantum computer, around 2029 is our goal. And then the middle to achieve that, it's as I mentioned before, you want to really master a single server rack or module and then network them together. We have some big results related to this coming out in the next month or two, which we're happy to talk about more then. But really, it's about networking and improving the core components, and that's really true for the industry overall. You want to be able to network a smaller quantum computer and to create effectively a larger one or a data center, and then everyone wants to improve all their key metrics as well. And photonics is no different. That's the hardware side of things. And now the software, as mentioned, is called PennyLane. It can be thought of as in two ways, really. PennyLane is kind of the open source software or the programming language for quantum computers, not just Xanadu's quantum hardware, but everyone else's pretty much around the world. And there's also the website, pennylane.ai, where you can now use PennyLane, and you don't have to store it, download it locally, but you can log in, kind of like an account you'd have on AWS. You can create your own profile and start working on your problems and demos there using PennyLane and save your work as well. So both of those things are going really well, and you can see some of the statistics here. PennyLane itself has had nearly 65,000 downloads per month and over 20,000 active users per month, which is quite incredible. And it's really building all the time. A lot of people just love it. Our team loves it. I think it comes out in the product and the community that we've built. In terms of the community, we've had a developer conference called QHack every February. And so far, the last 5 years, we've had over 10,000 participants to QHack. And now the other thing, the workforce is a very big thing as well. How do we train the next generation? We've seen the challenges when it comes to conventional AI. So what we've done from our side of things is PennyLane is taught in over 100 universities around the world now, and 33 countries. And that's really taught in quantum computing courses by the lecturer, where there's a module or a section on how to program quantum computers. And as mentioned, it's available on nearly every single major hardware provider out there. Number of users, you can think of them into three sort of chunks. One would be HPC centers. We work a lot with them. The quantum ecosystem, all the different sort of entities there, from startups to other organizations. And a lot of research institutions use it as well. And we find a lot of using it without us knowing. And that goes to the open source side of things. If you look at another indicator of its growth, is really on the number of publications and mentions in publications as well. So it's really grown, really significantly over the last couple of years. We anticipate over 1,000 mentions and citations this year alone. In terms of the training, again, you can see the different places around the world. It's really gone off on its product by itself now. Used everywhere. And as mentioned, you can see a list of the 33 countries around the world too. Nearly every major region has been represented in some capacity. And everyone that uses it wants to keep using it, which is what anyone wants to hear about a product that they like and have created as well. So I'll leave it there. A lot of information, and hopefully I can answer any questions that anyone may have as well.
Thank you, Christine. There are some questions in the Q&A. So the first one, let me read, or you want to read them by yourself? The first question is, are there any Xanadu initiatives which includes distributed quantum computing for horizontal scaling instead of vertical scaling?
Yeah, not at the moment. So if I understand it, everyone defines these things in a different way. I'm kind of thinking of, really connecting, say, two quantum data centers, 100 kilometers away or something like that. It's kind of the horizontal scaling. We're not thinking about that yet. We think we have our hands full already with just the vertical, or the sort of systems integration of a data center where it's networked. But if we make a lot of progress in the loss, all of that stuff will be needed for this horizontal scaling. So it'll kind of come very naturally for us if we do want to go that way. But at the moment, we're focused on just the vertical and quantum data center scaling side of things. I can
Okay.
see the questions if you want me to read them, or if you want to keep going, Lily, whatever's best for you.
Yeah, if you can read, just read the question and answer the question. That will be fun. Please.
Yeah, for sure. So, what possibility do you see in 1 million qubits in the near future? Well, I think in quantum chemistry, the overall answer is it's unclear yet. A lot of progress has been made by the Xanadu team and people around the world, but I think we're really, focusing on quantum chemistry, and that's not just unique to us. A lot of people in the industry are, and as mentioned before, we're focusing on, once you have 1 million qubits, how do you help identify in the work uh, workflow, where does it fit to help you with better candidates in creating new materials? But that's still a big question mark. And there's also the school of thought where you need a large data center, 1 million qubits. It's only then. Is there any plan for Africa? A great team in Africa, South Africa, who's sorry, just cut out for some. The questions have disappeared now. It just cut out for some reason, Lily. I'm not sure if you could.
Yeah, so you already answered the question about any plan for Africa.
Yes,
And
that's right.
yeah, then the next question is that does Zalando support the new startup in quantum computing? How can we collaborate?
Could you say that again? Does Xanadu support?
Quantum startups in quantum computing.
Yeah, we do. We love to work with anyone and everyone, really, if it's a win-win scenario. So, in terms of the startup community, we have worked with them and continue to do so. I would say it's mostly at this point on the software side of things and Penny Lane.
Okay. The next question is that is there a photonic-based quantum device which allows setting up quantum circuits or algorithms?
That allows what, Lily, to quantum algorithm?
Allows setting up quantum circuits or algorithms.
So for us, we do use quantum circuits, but we actually use measurement-based quantum computing, which is an architecture that's more suited to photonics, I would say. So yeah, quantum circuits, but it's equivalent to measurement-based systems. So those are easily mappable between them.
Okay, I think that's all the questions. So one person, thanks for your answer to the question. Let me see. Oh, yes, there's one more. So I
Oh,
think
I
we,
see. I can
yeah.
see them now. Yeah, the new ones.
Oh,
So how Xanadu is doing in terms of commercialization and revenue? So we have a small amount of revenue, single digit millions, but it's not our main concern at the moment. Our main concern is the hardware, getting to a quantum data center and working on with partners on things, which we do, get some revenue, but revenue will come if we can solve the loss issue and scaling up, and we'll be quite ready for large amounts of revenue if we can do that. So it's more of a focus and focusing on things that are more relevant. Obviously, commercialization revenue is relevant, but it's not relevant if you don't have a large enough quantum computer. So the other one is, what are the bottlenecks one can solve to assist you? Quantum optics guy. Well, loss, it's very easy, but very challenging. Easy to say, challenging to solve, it's loss. So if you look at any of our latest quantum computing papers on blueprints, wherever there's an optical element or light, there's going to be loss. So if you want to check out that sort of stuff, and you're happy to, if there's interest, please send me an email as well. Just to follow up, how can we access the measurement-based device on the cloud? What is it called? So it's called X8, but it's a very small version. We did have the quantum supremacy demonstration up, but it was up there for a year. So the only one we have up now is X8. Basically, that has 8 squeezes that's with an interferometer that mixes them, and then you have PNR detectors at the end. So you can't really do too much on that one. It's more playing around. Um, so and the reason we don't keep a lot of these online, forever, is it takes a lot of time for very good people to work on the stability and so forth as well. So the good people, their time is well worth focused on building out this fault tolerance.
Thank you, Christine, for your talk and for the great discussions afterward. And thank you all for joining us. The time is it's 2 o'clock. We should end this webinar. Thank you all.
Thank you, everyone.